Alright guys, so this morning what we're going to work on is biconditionals and good definitions. But before we get into that, I wanted to review what we did last week because you're going to use this as part of what we're going to talk about today. So here's the statement, and we're going to turn it into a conditional, converse, inverse, contrapositive. Please feel free to pause this video at any time. I kind of went ahead and wrote some of these sentences out to make the video go a little faster. So pause if you need to write something down and then start it up again when you're ready. So the original statement that I've given, an angle with measure greater than 90 is obtuse. There's actually two ways I could choose to write the conditional statement here that would both be correct, but let's go ahead and go through how I decided to structure it to start out with so we all have the same thing. Okay, conditional means just turning this into an if-then statement. So I wrote, if an angle measures greater than 90, then it's obtuse. Now, I actually said that was false because if you have an 180 degree angle that's classified as a straight angle, so that would be a counterexample. And then when I went down to the converse here, if an angle is obtuse, then its measure is greater than 90. Okay, so if I am an obtuse angle, that's the beginning assumption, my measure is greater than 90 degrees. So that's actually a true statement. The inverse switches the keeps the hypothesis and conclusion, but makes them both a negation or an opposite of what they were to start out with. So instead of greater than, I'm going to say if an angle measures less than or equal to 90, then it's not obtuse. That's true. If you guys remember, these two have the same truth value. And then the final, the contrapositive, switches the hypothesis and conclusion and makes both opposites. So your contrapositive, it's going to say if an angle's not obtuse, then its measure is less than or equal to 90. And again, I'm just going to use 180 degrees would be an angle that's not considered to be obtuse. It's considered to be a straight angle. These two, the conditional and the contrapositive, always have the same truth value. And if you use a counterexample for one, the same counterexample will work for the other because they're logically equivalent. All right, now what we're going to get into today did not happen in this example up here, and that is what a biconditional is. So a biconditional is something you can write when a conditional and its converse are both true, and what you can do is combine those into what we call a biconditional. I'll show you how to do that down in example 1, and you combine them in the middle with what the phrase is right here, if and only if. The symbol form of this, hypothesis is P, conclusion is Q. The arrow actually works both ways, and the way this is read is P, if and only if Q. Now the only way you can do this is if the conditional and the converse are both true, and oops, I missed the if on this. The abbreviation I'm going to use for this in some sentences to save us some time is IFF, to stand for if and only if. Okay, so down in example 1, remember, pause this if it's going too fast. I know you're writing sentences out. So in example 1, we're going to decide, okay, is the conditional true? Is the converse true? If it is, both situations, we're going to combine it into a biconditional. If it's not, we're not going to combine it into a biconditional, and we're going to state which one is false and use a counterexample. So first one I have here says if two angles have the same measure, then the angles are congruent. That's true. If two angles are both 90 degrees, then they're both going to be congruent to each other. If I flip that around, if two angles are congruent, then they have the same measure, and that's also a true statement. If they're congruent, the measures are the same. So since both of these statements are true, I'm going to write down a biconditional. Now, you can write it in the order of the original or in the order of the converse. It doesn't matter. For this particular one, I went ahead and just used the same as I did for the converse. But you'll notice the if and the then disappear, and it's going to be taken care of in the middle of the statement. So this says two angles are congruent. That's just the symbol for congruent. If and only if they have the same measure. You could also write that as if two angles have the same measure if and only if they are congruent. So it works both ways. All right. Now, hopefully there's a little bit of familiarity to you at this point with an example that's got an absolute value, but here I said if x equals 4, absolute value of x is 4. That's true, because I'm assuming the absolute value of x is 4 after I have plugged in 4 to that equation. So we're assuming x is 4. The converse flips that. Now this says if the absolute value of x is 4, so I'm starting with the equation, then x had to be 4. That's not true because that equation actually has two answers, 4 and negative 4. So we cannot write a biconditional here because the converse is false. And so I go ahead and write a counter example. You can only write a biconditional if the converse and the conditional statement are true. All right, this is the example at the top on the back, and this is to actually take a biconditional and separate it into its conditional and converse. And again, there's two ways you can do this. I usually try and just go kind of in the order of the biconditional that they give me. So this says lines are skew if and only if they are non-coplanar. So we're going to turn this into an if-then statement. If lines are skew, then they are non-coplanar. That means they're not in the same plane. Can always draw a plane to create parallel lines, but if you can't draw a plane, then you can't have parallel lines, so they have to be skew. So this is true. If lines are non-coplanar, so if lines aren't in the same plane, then they're skew, they're not intersecting, they're not parallel. You can't draw a plane between them. So both of these statements are true, and we're just separating that biconditional into those two statements. Now for part B, this is actually the one we used on the front, and I can turn this into a biconditional, but I have to add a little bit more because we talked about the 90. So an obtuse angle actually has to be between 90 and 180. So it's greater than 90, but it's less than 180. So if we add that in there, this is a true biconditional. And writing these two sentences, I went in the same order as the biconditional when I created the conditional here. If an angle is obtuse, then its measure is greater than 90, but less than 180. And then the converse to that is if an angle is greater than 90, but less than 180, then it's obtuse. And feel free to use symbols as you're doing these to kind of abbreviate. And pause the video if you need to. I'm going to slide this up. Now, the whole idea behind a biconditional, it's what we can turn into a good definition. So just 3 things you have to have with a good definition. Use clearly understood terms. Make sure it's precise. We're not going to use words that are vague, like large, sort of, some. It has to be very precise. And a good definition is reversible, meaning the conditional and converse are both true, and so it can actually be written as a biconditional. All right, so in example 3, I've got a definition that we are going to show is a good definition by thinking through the conditional, the converse, and then writing it as a biconditional. If you have a good definition, it can be written as a true biconditional. So it says a triangle is a polygon with exactly 3 sides. Okay, so conditional. If a polygon is a triangle, then it has exactly. When you see the word exactly, it means only, and so that's important here, 3 sides, because I could have 3 sides and be a square, because I have at least 3 sides in a square. We just have a 4th side. So when it says exactly, it means only that number of sides. If you flip that, if a polygon has exactly 3 sides, then it's a triangle, also true. And then the biconditional, I just went ahead and went in the order of kind of the original statement they gave us. A polygon is a triangle if and only if it has exactly 3 sides. Okay, now at the bottom, you don't have to completely write these out, but I've got a statement, and I just want to think through whether or not this is a good definition. So if it's a good definition, the conditional and the converse of the statement would both be true. So again, you don't need to write these out, but think through them and be able to write a counterexample if you say it's not a good definition for either the conditional or the converse. Now, I went ahead and wrote them just so you guys can see here. If a fruit's an apple, then it contains seeds. That's true. If I'm an apple, I have seeds. But if I do the converse to that, if a fruit contains seeds, then it's an apple. So that's actually not true because I can think of tons of different fruits. I just used a lemon as an example here that have seeds. So this is not a good definition. We could not write this as a true biconditional. You're going to see the same thing over here. A square is a figure with 4 right angles. Is this a good definition? I don't think it has enough information when you start to think through the conditional and the converse. First I wrote a conditional. If a figure is a square, then it has 4 right angles. That's true, but if I turn that around, if a figure has 4 right angles, then it's a square. That's actually false, because I could think of a shape called a rectangle that would have 4 right angles. You could have a larger figure. You could have an octagon and maybe 4 of the angles in that octagon were right angles. That's a possibility. So this is not a good definition. It's not specific enough. So now you guys are going to work on your homework and do your best with the biconditionals and the good definition.